Hello everybody and welcome to this short tutorial on RF and microwave measurements. My name is Erikos Lourandakis and my passion on microwave measurement techniques and equipment comes from my background as a microwave engineer and lab administrator both in academia and industry. You can find more information on this material at my homepage lourandakis.com. Let's begin with the basics of AC signal analysis. We consider therefore a time-variant voltage signal that is applied on a load resistance. A sinus wave in the time domain is represented in the frequency domain as a single spectral line. Signal relations are often described in decibels with respect to voltage or power ratios. Absolute power levels are usually expressed in dBm as the power ratio with respect to 1 mW. The link between the time and frequency domain is established by a mathematical operation called Fourier transform, or simply FT. The Fourier analysis allows for an expansion of the periodic function f with weighted sine and cosine functions. The Fourier coefficients a and b are determined in such a way that the infinite series is identical with the function f. Both the Fourier and the inverse Fourier transform are powerful tools for signal analysis. A signal spectrum is defined as power over frequency and is the basic representation when considering frequency domain analysis. The measurement equipment used to capture a spectrum is known as spectrum analyzer. On the other hand, a time domain analysis is performed with an oscilloscope, where voltage signals are displayed over a certain period of time. Both domains are somehow complementary, and each one has unique advantages and helps us to analyze different phenomena like signal distortion, harmonics, and phase relations. Let's begin with some basic principles of microwave network theory. There are two major network types, namely linear and nonlinear networks. For linear networks, the input and output frequencies are identical. The output signal simply undergoes amplitude and phase change. Linear networks can be characterized by their S parameters, as measured with a network analyzer. On the other hand, nonlinear networks may have a very distorted output spectrum. Multiple harmonics and mixing products may be present at the output terminal of the device under test. In this case, small signal network analysis, as described by S parameters, is no longer valid. A spectrum analyzer is basically a sweeping narrowband receiver. The RF input signal is passed to an input attenuator, which is used to adjust properly the input power level and protect the mixer from overdriving. Low-pass filtering is performed prior to the mixer in order to cut off the image frequency from the input signal. The RF signal is downconverted to the intermediate frequency IF by a variable local oscillator frequency. A sweep generator produces the required frequency ramp and also drives the horizontal frequency axis of the display. The downconverted signal is leveled by an IF amplifier and filtered by a variable bandpass filter, which determines the resolution bandwidth of the spectrum analyzer. A logarithmic amplifier is following, and at the power detector, the envelope of the signal is captured. The detector output is passed through a low-pass filter, also called video filter, smoothing the signal before it gets displayed. At this point, we end the tutorial on RF and microwave measurements. I hope you found the material interesting, and if you have any questions, please feel free to contact me through the web at lourandakis.com or directly via email. Thank you for your attention.